Hello everyone and welcome back to FE exam preparation for mechanical engineers. In today's statics video, we are going to be doing an overview of friction and two practice problems. Friction opposes the relative motion or tendency of motion between two surfaces. So recall from your statics or physics class that we have two kinds of friction. We have static friction, which acts before an object even begins to move, and the coefficient of friction for static friction is mu s. Whereas for kinetic friction, this acts after an object begins to slide, and the coefficient for kinetic friction is mu sub k. So if we were to draw a graph between the force of friction and force applied, so force applied, force of friction, you'd see something like this. Where this peak here is the slip point. So if we're applying force and the force of friction is constantly pushing against that force, right? It's only going to work as hard as it needs to counteract that force applied. So a lot of times students don't understand that the force of friction is not always just equal to mu times the normal force, right? It's going to be equal to whatever the force applied is up until we are in pending motion or at the slip point. So FF equals FA all the way up until this point here. That is where the force of friction is going to be equal to mu s times n. And then once we go past that point and begin to slip, we're going to drop down a little bit and then be at the force of kinetic friction this entire time, and that is going to be constant. Right, so that is sort of how to visualize the differences between static and kinetic friction, and understanding that the force of friction is not always equal to mu times the normal force. And you'll see that here in the key equations. So for static friction, this is where the force of friction is less than mu s times n. Impending motion is where the force of friction is equal to mu s times n. And then the force of kinetic friction is equal to mu k times n. Note that mu s will always be greater than mu k, right? Okay, so let's move into a practice problem now. We are asked to determine the force of friction required to keep the box from sliding down the incline. And we are given the mass of the box, the degree of the incline, and the coefficient of friction between the surface. So this is definitely one of those problems that you've probably seen in your beginner physics course or even in statics. And it is a highly likely sort of difficulty of problem that you could see on the FE exam. So it's good to just know how to do one of these basic problems for friction. There's not much more that they can really do, right? The other kinds of problems that you would probably want to practice are maybe a tipping problem. And we can even go over one of those in another video. So to begin with this problem, we're going to want to start out by drawing our free body diagram. So I'm going to just draw my incline, like so. This angle here is 30 degrees with respect to the horizontal. Here is my box. Okay, so we are going to have a normal force which is perpendicular to the surface. We are going to have the force of friction pointing up the incline because it is opposing the block wanting to slide down, and the weight of the box itself, mg. Now, I'm going to want to tilt my coordinate axes. I'm not going to have a normal Cartesian coordinate plane, because by doing this, I'm essentially aligning the normal force and the force of friction, right? These two are now, this one is aligned with the x-axis, and the normal force is aligned with the y-axis, right? So that eliminates two of the forces that I have to resolve into their components. Now the only force I have to break down into components is mg. And that is exactly what we are going to do right now. So if I take mg, I'm just going to move it over here, right? I can make a triangle, right? Just normal vector math here, where this angle here is my theta, right? Some triangle theorem, not sure which one, but it states that this angle here must align with this angle here. If you can memorize that, you will be golden for the exam. And I'm sure at this point that you've done enough of these problems with the incline box on a ramp that you understand that that is the angle for your decomposition of the weight vector. Okay, so simple SOHCAHTOA, this is going to be mg cosine theta, and this is going to be mg sine theta. Okay. Now I am set up and ready to do my sum of the forces in the x and sum of the forces in the y. So let's do that. Sum of the forces in the x is equal to 0. So by that we are saying that the mg sine of theta minus the force of friction is equal to 0. All right. This is pointing positively down the ramp with how we define the coordinate axes here, and your force of friction is obviously opposing that. So that's the sneaky sideways force that is sort of making the block want to slip down the ramp. Even though there's no force applied, it's there. Okay, so now if we do a sum of the forces in the y and set that equal to 0, we will get that the normal force minus mg cosine of theta is equal to 0. So now we can solve for the normal force. That's just going to be equal to mg cosine of theta, which is equal to the 20 kilograms times 9.81 times cosine of 30 degrees. And that comes out to be 169.914 newtons. Okay, this value is important because that is the value of our normal force. And that is a value that we are going to directly plug in to the force of friction. All right, cool. So if we do now, the force of friction is equal to mg sine of theta, we will get that this is 20 kilograms times 9.81 times sine of 30 degrees. So therefore, we are getting that the force of friction is equal to 20 times 9.81 times the sine of 30. 98.1 newtons. But wait, where did you use the normal force in this calculation of the force of friction? Well, this value here is the force of friction that is required to keep that box from moving. So required to keep block still, right? That is the value that we need to have our force of friction be in order to keep it from moving. Okay, well, how do we check that? Well, because we are assuming that we're impending motion, right? Because we can't have the block move, we need to check and see that the value of mu times the normal force is greater than that force that is required to keep the block still. So basically, we are checking if mu s times n is greater, I should flip this arrow, greater than this value. That is essentially what we are doing. Oh, I didn't mean to erase. Okay, now let's do that. And I'm going to do that over here in this corner here. So remember that force of friction is equal to mu s times n. So we're going to take 0.4 times that normal force value that we found, 169.914. And it unfortunately is less, 67.97 newtons. Okay, so what does this mean? Well, essentially, this means that the angle or the surface that you have this block resting on is not optimal. So we could fix this problem and have the block stay by decreasing that angle of the incline, or by picking a rougher surface for this block to sit on. So right now, at this angle, you cannot place the block without having it slide. It will begin to slide no matter what. It will not stay still. Okay, that is what we determined. So if you get a question on the FE exam where it's like this, and maybe it's a multiple choice question and they give you a couple of values, or it says the block will slide, something like that, then you know what to put. Okay, and that is sort of how you check and make sure that you are doing these problems correctly, sort of the logic behind it. Okay, let's go ahead and move on to the next one. So for this problem, same setup, except this time we were asked at what angle will the box begin to slide down the incline. So now we get to figure out where we can optimally place our incline such that the block will not slide. Okay, so same setup. We're going to have a free body diagram. All right, with our coordinate axes tilted. And here's my incline. We're at 30 degrees. This time, I'm not going to go ahead and do that whole process of breaking down the forces. I'm just going to say that this is mg cos theta. This is mg sine theta. This is the normal force, and this is our force of friction. Okay. Going from here, sum the forces in the x to be equal to 0. We get that mg sine theta minus our force of friction is equal to 0. Okay, we sum the forces in the y direction equal to 0. Remember, this will just be that the normal force is equal to mg cosine of theta, where that n value will indeed not remain the same because we have a different theta value. That is what we are solving for. Okay, so because we know that this is going to be impending motion, right? That is our case here. Impending motion. So recall, for impending motion, FF is equal to mu s times the normal force. Great. Okay, so we can go ahead and use this in the sum of the forces in the x equation and say that mg sine of theta is equal to mu s times the normal force. Okay, cool. So then now all we need is to get this equation into terms of common variables, right? We don't know what n is, we don't know what theta is. We do know m and we do know g, right? So all I'm going to do is plug in this for n, right? Just a simple substitution method here for two equations. So this simply becomes mg sine of theta is equal to mu s times mg cosine of theta. All right, what's sweet about this now is that these mg's, because they are on both sides of the equation, they can cancel out. So then we are left with sine of theta equals mu s cosine of theta. Divide each side by cosine of theta, we'll get sine of theta over cosine of theta is equal to mu s. Take that a step further, sine over cosine, that's a tangent. Tangent of theta is equal to mu s. And to reduce that even more, we get that theta is equal to the tangent inverse of mu s. Okay. Going from here, plugging everything in, plugging in 0.4 for that mu s, theta will be tan inverse of 0.4, which is 21.8 degrees. And that makes sense because at 30 degrees, our force of friction was not sufficient to keep the block from sliding. At 21.8, that is the absolute maximum we can have our incline be at before the block begins to actually slip and slide down the ramp. Okay, so in conclusion, with these friction problems, it is very important to understand what case you are working with and what you are looking for, right? For this case, I knew it was an impending motion case because they asked about when or at what value of degree angle will the block begin to slide. So you got to look at the wording of the question. Whereas this question was just to simply determine the force of friction required to keep it from sliding. Yet another impending motion problem, but we had to solve for our force of friction required to keep the block from moving and then compare it to the absolute maximum force of friction that this surface can have, right? Given the values. So understanding how to think through these problems and even doing these two are extremely good practice for the FE exam because they're not going to be extremely in-depth problems. So I hope that this helps. If you like this video, please drop a like and subscribe to the channel. It helps us out a lot. Let us know in the comments below if you'd like to see any other friction problems or any other videos in general. We'd love to hear your feedback, and we will catch you on the next one.